Hello everyone, this is Astarag and I'm starting a new series on this blog post called as How to Scale Your Model, a systems view of LLMs on TPUs. Here we'll be going through each chapter, the what examples, and we'll be trying to deconstruct everything and understand the content of this blog post. It is a multi-part series and we'll be going through each of the topics slowly. Let's start with first two chapters. Before jumping into rooflines, let's first discuss these two concepts. One is flops and another is flops with lowercase s. I always get confused by these two terms. Flops with capital S means floating point operations per second. Floating point operations are the multiply and the additions that a ALU unit in a computer can do, and how many operations can you do per second. Flops with lowercase s is the number of floating point operations. So the relation is flops with capital S is equal to number of flops you can do per second. For example, NVIDIA H100 can perform almost 10 E14 BF16 flops or floating point operations per second. Then the next concept here is called as time taken for compute. It is the number of computation, like for your algorithm that you're trying to implement, how many computations are you doing per second divided by the accelerator floating point operations. The example that we saw in the last slide was for NVIDIA H100, which can perform on almost 10 E14 BF16 flops. And this goes into the denominator here if you're using a H100 for calculating the time taken by our computation. So suppose you are doing 1 E to 12 flops. So your total time taken is 1E12 by the NVIDIA H100 flops, and it will take around 1.1 milliseconds. Then the next concept is time taken for communication or communication bytes by the bandwidth of our accelerator. And the numerator is basically how many bytes we need to read and write back to our memory while doing our operations. And the denominator comes from the spec sheet of a NVIDIA GPU or a TPU from Google. The bandwidth is basically how many bytes can a device transfer. So this is a diagram of NVIDIA where you have a group of 8 GPUs which are interconnected with NVSwitch and NVLink Fabric, and if you want to go across like connect two clusters of this, then you go through this special purpose accelerators called as NIC, which will transfer data from this node to this node by InfiniBand switch. And this came from NVIDIA's acquisition of Mellanox. And NICs are basically a way to sidestep CPU. Earlier, people used to transfer the data from GPUs to the CPUs, and the CPUs were responsible to transfer into another node. But with NICs, you can directly, a GPU can talk to another GPU over this InfiniBand switch. So, and these numbers are the bandwidth of, like, you can see, like, as the distance from the device increases, your bandwidth starts to reduce. And within a node, you can transfer data really fast, but across a node, it takes a ton of time because of the reduced bandwidth. So we will be plugging this to the denominator of T communications. Another concept that we are going to see in this first chapter is overlap and non-overlapping communication and computation. In an overlapping setting, So as you are loading the bytes, you are doing operations on them. And it is async, like you get some amount of bytes, you do operations on them, and then you get the next set of bytes, you are doing operations on them. But if it is blocking or non-overlapped, so you have to wait to load all the bytes and then start doing operations on them. And in that case, like your total time would be the total time to do operations plus the total time it took you to load the data. So this should have been comms. I'll fix this in the slides later. But yeah. Now, the next topic that we are going to discuss is arithmetic intensity. It is the ratio of total number of flops an accelerator performs to the number of bytes it needs to communicate. So per byte loaded, how many operations you are doing. And we can compare the arithmetic intensity between your algorithm and the and what our accelerator is offering us. And if you compare between these two, then you can say either you are communication bound or you are compute bound. So the arithmetic intensity is computation flops, how many floating point operations per second, by the communication bytes, how many bytes you need to transfer to do those operations. And this includes both read and write. Let's see an example of dot product. Suppose you are doing a dot product between two vectors, ABC and DEF. So in dot product, you multiply these two, this two, this two. And you have 3 multiplications and then you need to add them. So you have 2 additions. So for n equals to 3, a 3 length vector, you need 5 operations total, which is also 2n minus 1, where n equals to 3. This is the computation flops. Now communication bytes, or how many bytes you need to transfer. So BF16 has 16 bits or 2 bytes, 1 byte equal to 8 bits. And the total communication is you need to read, here n is equal to 3. So each one is BF16. So you need to read 2n number of bytes and another 2n number of bytes. So total of 4n number of bytes you need to read, and then you just write back one answer. So this materializes into only one scalar value and you need to write it back. So if you see the arithmetic intensity, so this is 2n minus 1, which comes from here, the number of computation flops, and this is the number of read and writes, which is equal to 4n plus 2. And this materializes into 1 by 2. The worst part here is it is always constant. So no matter if you increase your bandwidth or you increase your bandwidth or increase your computation flops of your accelerator, this is not going to be affected by that, because the arithmetic intensity is constant. Now let's see matrix multiplication. In matrix multiplication, you take this, you have a matrix, 2 matrices of dimensions B, D, D, F. So what you do is you multiply this row with this column, then this row with this column, this row with this column, and you get one row for the you get one row in your result matrix. So if you see the number of operations you are doing here, it is, so this row is of length D and this is of length D. So you will be doing 2D multiplications. So each elements get multiplied here, 2D multiplications, and you will be doing, one mistake here is this has an extra number of rows. So let me fix it. Let me fix it in the post slides. So yeah, this should be the equal number of rows, equal number of columns and rows. So you will be doing D multiplications and D minus 1 additions. So this is basically a dot product between these two entities, these two this row and this column. And you need to repeat this b times, and you need to repeat this column f times. So total number of operations is 2d minus 1 bf, and you can for simplicity you can ignore this minus 1, so it is almost 2 bdf. Now if you compare the number of how much you have to read and write back, so as I said, this is bf16, so it is 2 bytes. So you need to read b into d, b into d and d into f. So that would be, this 2 comes from bf16, so you need to read 2bd and 2df. And while writing back, this resultant matrix multiplication produces bf matrix, b and f. So you need to write back to bf. So your arithmetic intensity is 2bdf, which we got from here, and your total, this is your read and this is your write. So this which we calculated here, so your arithmetic intensity is of this shape. So if you see here, it is O(n) cube by O(n) square, which is not a constant, and it scales with your dimensions of your matrices. So you can so now you can actually control by your dimensions of matrices, you can control the arithmetic intensity. It is not constant like what we had in dot product. And one of the example which I found really interesting in the blog post was this question 4, and here you were performing a matrix multiplication between this b comma d and b d f, and which results in a matrix of b comma f. So it was asking about the arithmetic intensity of this operation. So here also the computation flops remains the same, and but the read and write, as it is integer, so there is no factor of 2. The read is bd, bdf from here, and then you need to write back bf. For this operation, this is not a matrix multiplication. For this operations, you can see like it is also a constant, and it is scales by factor of 2. So you don't have any control over changing the shape of dimension of matrices, or changing any of these values to control the arithmetic intensity. So this is going to remain constant. So I built a few visualizations for understanding arithmetic intensity. Let's first go to dot product. We saw in our slides that, where was it? Yeah, in dot product it scales constant. So if you see here, so you have your t memory or t communication, and then your t math or t compute. So if you see this is remaining almost constant ratio. So you can, here you can control the d vector. So you can see you can increase the vector length, but still the communication and the computations, they don't converge, or they do not cross each other. So they are going to, the ratio between these two lines are always going to be constant, and it is constantly going to keep on increasing, because it is the arithmetic intensity is constant. You can change anything like the precision, you can change it for still the equivalence remains the same. But now if you go to matrix multiplication, things start to change. You get clear separations between compute bound and memory bound. Let's first go through this UI to understand what's happening here. So in the sidebar, we have matmul shape, which is b, whatever shapes we saw in our examples here, like all these examples. We are just seeing them here, which is B. Let me see if I can increase, which is B, D, and the hidden dimension. So I wrote this with respect to transformer, but you can treat them as constant variable lengths that we'll be using to do matrix multiplication. And here you can control different precision. FP32 has 32 bits, and as I said, 1 byte equal to 8 bits, so this is 4 bytes, and BF16 is 2 bytes. You have FP8, which is 1 byte, and integer 8, which is also 1 byte. And you have different accelerators that you can choose. So let's say you choose H100 SXM. So here you can see all the vendor pick spec sheet. The specification said for H100 you have floating what the accelerator offers you. So H100 can do this many operations per second for BF16, and it can and it has also certain bandwidth. Um, Sorry, this is the bandwidth, and you can see here, like, if you move to FP32, the number of floating point operations per second reduces by half. But if you move to something like int8, then your floating point operations almost doubles as compared to BF16. So so when you reduce the precision of your data, then your floating point operations increases. Floating point operations per second increases. So you can select other hardwares here, TPU B5E, and you can see their peak compute floating point operations per second for BF16, and and this is for int8, and the memory bandwidth. So this visualization is trying to find is trying to plot the arithmetic intensity. Let me go back. So this is what we went through the entire lecture of. The arithmetic intensity is like 2BDF is your number of operations you are doing, and you're reading BD plus DF, and you're writing back BF, and this S is your precision. So if you have integer 8, so this value is 1, how many bytes? If you have BF16, this value is 2, and if you have FP32, your value is 4. So you can see here, for B of value 5, I'm lying in this region, which is called as memory bound. So another thing that you need to notice, let me do a full screen. So remember this, I choose let me choose H100 SXM, and this has this peak compute, and this peak compute is for int8, and this is the memory bandwidth. So if you have to calculate the arithmetic intensity that this device can provide you, you just take this value and divide with this value, and you will get this rich value here. So this is your accelerator's arithmetic intensity, how much it can provide you. So this goes into the y-axis, and in your x-axis you are toggling the this b variable to see if you increase it or decrease it, where you can achieve where you can lie in this compute bound range. The reason we are trying to do this analysis is memory is expensive. So if you are in this region, you will be spending, your accelerators will be spending a lot of time being idle. They won't be doing any operations. But if you get the elements or the data to the compute units faster, then you can take advantage of increasing flops. NVIDIA always increases doubles or triples the flops that you increases the flops exponentially in every generation, but the memory remains constant. So so you would love to be in this region, and in transformer, which we'll be discussing in the subsequent lectures, this D and F are your architecture. It's your transformer architecture. Those are not going to change. Your architecture is not going to change. So the only control knob you have is how many tokens you are processing at once, and that is your variable B. So you can see if I here my B is let me enlarge it. So here my B is 5. So you can see I'm clearly memory bound. So this also goes into when you are doing inference and you are doing only one, you're serving only one request per second, where your batch size is equal to 1, you lie in memory bound range. And as your batch size would start to increase, you will start to go into the compute bound range. So let's see an example. So I'll keep on increasing the batch size. You can see my uh, my this dot is approaching the ridge here. It's trying to approach the ridge, the maximum computation uh, that per second that the device can offer you. So it is starting to go up really, really fast. So yeah, this one, let's try a value 260. So it's still not there. So let's see how much. So around 295, 300, it reaches this reach point value where it has an intensity that is close to what our accelerator is providing us. Beyond this point, you will be beyond this batch size of where you got this optimal batch size. You are now in compute bound region. So you are getting the data really fast to the compute units, and now it is now you are bottlenecked by how fast the computation is being done by your compute units. So similarly, things change. Now I was in precision integer rate. Let's see if I am precision in FP32. See what changed. Uh, if I go back just for a second, integer rate, look at this ridge value. It was around 590. Now, if I go to FP32, look at this ridge value, which is 148. So what happened? So in FP32, this S parameter is almost is 4. You have 4 bytes. So your accelerator intensity has reduced now by a factor of 4 as compared to int 8. So you are going to reach the compute bound. So you will be reaching the compute bound range when you all hit this intensity of 148. So this is the trade-off that you are doing when you are keeping your intensity high or the precision high or low. So if you see now, if I do BF16, the ridge value increases to 295, and which is almost double. And if I FP8 is the same precision, and int 8, when I do this, your ridge value increases to 590. So so this is the trade-off that you pay when you have different precisions. Like when you separate between memory bound and compute bound, that bar decreases as you increase the precision. So if I have a precision of FP32, so you can see like you reach this intensity, like your intensity with the similar batch size, you have lower intensity. And so we discussed so feel free to play around this UI to understand how the compute intensity varies with all these knobs. Let's